So let us start with this one. We'll be trying to complete all these three chapters: 1.5.1, 1.5.2, 1.5.4 according to the new syllabus. Alright, so starting off with the definition of force. Generally, in our middle school, we studied or defined force as a push or pull. At this stage, ever since they have included the topic momentum, now we try to define force in terms of momentum. Matter of fact, in A levels, you have to define force in terms of momentum. So here we define it as the rate. Force is the rate of change of momentum. This is how we define force: the rate of change of momentum. And when we use the word rate of change, it means the change in momentum with respect to time. This is what the word rate stands for. Then we have the next thing. So just let me write it down. Rate means with respect to time. So this very statement can also be written as the change in momentum with respect to time. That would be the same thing. Now, talking about the force, force has certain properties. Force can change the shape, it can change the size, and it can change the state of motion of an object. And changing the state of motion itself has different cases. For example, if an object is moving slowly, the force can make it move faster. If an object is moving faster, the force can make it move slower. If an object is at rest, object is not moving at all, the force can make it move. And if an object is moving, the force can make it stop. So it has different cases. But it is generalized as the force can change the state of motion of an object. Now, the unit of force. The unit of force is newtons, which is represented by the capital N. Right? Like I said, in physics, all the units which are named after scientists are represented by the capital letters. So when we represent the Newton, we represent the N with the capital letter. Now, the instrument that can be used to measure force is called spring balance. S-P-R-I-N-G, spring balance. It is also known as the very same instrument. It is also known as Newton meter. So generally, these are calibrated in newtons, and we just hang the object with these balance, and it would give us the value of force, like how many newtons of force is being exerted by the object, by the earth on that object. So, matter of fact, there is a special kind of force which is generally measured by using this instrument, and that force is weight. I mean, we can also measure the pushing force or the pulling force with the help of spring balance, but we prefer to measure a certain kind of force with the help of spring balance, and that force is weight. And it should be clear at this stage that weight is nothing but a force. Weight is also measured in newtons, so is a force. Examples of some of the forces are friction, weight of an object, air resistance, which itself is a kind of friction, electrostatic force, magnetic force, electromagnetic force, gravitational force, and stuff like that. The next thing that we have is contact force and non-contact force. Contact forces are the forces that come into existence when objects are in contact. So at least there has to be two objects. And non-contact forces, they exist even when an object is not in contact with another. Examples: pushing force. You have to push an object, it means you have to touch the object. So the push, pull, if you have to pull the object, you have to touch the object. You have to make contact with the object. Friction. Friction exists only if two objects rub against each other. Otherwise, the friction won't be there. So these are some of the examples of contact forces. Non-contact forces. Magnetic force, electric force. You have a magnet, all right, you place a magnet somewhere on the table, and then you bring a magnetic material close to it. The magnetic material will be attracted towards the magnet even if the magnet is not touching that material. So is the gravitational force. I mean, even if Earth is not touching an object is in the air, still if you leave the object, it'll be attracted towards the Earth. So gravitational force is also a non-contact force. For the contact forces, matter of fact, for the non-contact forces, there exists a field or a field exists. For example, if we talk about the magnetic force, it is there due to the magnetic field. Electric force is there due to the electric field. Gravitational force is there due to gravitational field. So there is a field. Field is a region in which the object would experience that force. For the contact force, there is not any field. Then there's the force that is the tension. The tension force exists whenever an object is being pulled generally with the help of a string or with the help of a rope. So it exists in cables, ropes, and strings. The tension force. The direction of the tension force is always away from the point of application of force. and I'll explain this one, away from point of application of force. You see, in this case, the person is applying the force over here. The second one on the right side, is applying the force over here. The direction of the tension force is away from this point. So for this guy, the tension force would be on this side, and for this guy, the tension force in the rope would be on this side. This is a point of application of force. These are points of application of forces, and the tension force is always away from that point. The next thing that we have is the balanced forces and the unbalanced forces. So balanced forces means no net force. It means no net force. And if the object is balanced, the object might be in two possible states. Generally, the students think if the forces are balanced, the object would be at rest. No, it can exist in two possible states. Yeah, one of them is the object might be at rest. Object is at rest. Now, what are the examples of that case? For example, this person sitting on the chair. The person is applying the force downward on the chair in the form of weight of the body. As a result, or in consequence, the chair is applying the same amount of force in the opposite direction. The chair is pushing the person in the opposite direction, that is upward. So if the weight of the person is, let's say, if that guy is kind of 50 kilograms, so its weight would be approximately 500. So if the weight is 500 downward, the chair has to apply 500 upward. Only then the person can sit on the chair. If the chair is unable to apply that force, then it will be broken down and the person would fall on the floor. So all of these are examples of balanced forces. There's another situation. If the forces are balanced, then the object can be moving as well. But the thing is, if it is moving, it would be moving. Object moves at constant speed. The object would be moving with constant speed in straight line. So if the object is moving, then the object would move with a constant speed in a straight line. That is also called constant velocity, because if we add a certain direction to the speed, that becomes velocity. Now here's the situation. If the forces are balanced, the object can be at rest, or the object might be moving at a constant speed. If the forces are balanced, the only thing that is not going to happen for the balanced forces is object accelerating. That is not going to happen. If the object is accelerating, when I say accelerating, it can mean deceleration as well. If the object is speeding up or slowing down, or accelerating, decelerating, the forces can never be balanced. Now here are the situations for the balanced forces. The person or the parachutist falling with a steady speed. Now the weight of the person is downward, and its weight might be, let's use the same one, 500 Newton. And there's another force acting upward, that is a friction, which is also 500 Newton. And these two forces would be equal. And if these two forces are equal, which makes them balanced forces, then the person would be moving with a constant speed in a straight line, or it would be moving with a constant velocity. Another example is when you sit in a vehicle or a car on a motorway and you're moving with constant speed on the motorway. Let's say with a speed of 60 might be like too little, 80 kilometers per hour. You're sitting in the vehicle, there's no jump, there's no bump on the road, you're moving in a straight line, you're not changing the lane at a speed of 80 kilometers per hour, you're not changing the speed, like not even a little bit. You would feel as if you're not even moving. It appears. If you're not speeding up, not slowing down, you're moving at a constant speed, constant velocity, you'll observe or you'll realize that as if you're not even moving. Matter of fact, you'll notice the movement only if you speed up or only if you slow down. So when you were moving at a constant velocity, the forces were balanced. What forces were there? Mainly the forward force of the engine and the backward force of the air resistance. These are the horizontal forces that were there. All right, moving on to the next thing. If the forces are balanced, if the forces on the body is balanced, then once again net force is 0. And you find the resultant force. The resultant force in the first case would be 6,000 minus 6,000. Two forces, equal magnitude in the opposite direction. The answer would be 0. With 0, you can write Newton, or you can just not write Newton. The second case, the resultant force, F resultant equals 500 minus 500, and that would once again be 0 Newton. Then we have the next thing, the Newton's first law of motion. Now, first of all, Newton's first law of motion corresponds to the balance forces. And according to it, if an object is at rest, if the forces are balanced, then if an object is at rest, it stays at rest. And if an object is moving, with constant velocity, it keeps moving with the constant velocity. Keeps moving with a constant velocity. Or if you want to write in terms of speed, then you have to add in the straight line. Or you can say if the object is moving at a constant speed in a straight line, then it keeps moving with a constant speed in a straight line. Newton's first law of motion also provides the situation for equilibrium of a body. And equilibrium is a state when two conditions are to be fulfilled. Number one, no net force acting on the body. No net force on the body or on the object. Second one, no net moment of force on the object. No net moment of force on the object means no rotation in the object. So moment of force is the same thing that we studied previously, turning effect of force. So the first condition of equilibrium, once again, it was no net force. On the object. So it doesn't mean that there should be no force should be acting on the object. There can be the forces acting on the object, but the thing is the resultant force or the net force should be zero. So no matter how many number of forces are there, their total effect or their resultant should be zero. So you see, in this situation, on this object there is no net force. We assume that all these forces cancel out each other in a certain way. So no net force. And if there is no net force, it will satisfy the first condition for the equilibrium. Now the thing is, let's say I remove one of these forces. I remove this force from here. Now, if I remove that force from here, the object would no longer be in equilibrium. There would be motion in the object. And then the question is, where would the object move if you remove this one force from here? And the answer is, the object would move in the opposite direction to the force that is removed. Exactly opposite to F2. If you remove, for example, if you remove the force F1, the object would move in the direction opposite to F2, because F1 was there and it is one of the components that is keeping the system at rest. If you remove that one force, means there's nothing that is making it stop in that direction, so it would move in the opposite direction. So here we have a sample question, and in this one we need to find the missing forces. Now you can break it down into x-axis and y-axis. It is given that the system is in equilibrium. It's written over here. The system is in equilibrium. If the system is in equilibrium, the resultant of all the forces should be zero. And that can be broken down into two things. The resultant of the horizontal forces should be zero, and the resultant of the vertical forces should be zero. Now, how many horizontal forces are there? 1, 2, 3, which is the unknown. So the sum of all these horizontal forces should be zero. Then the thing is, how many vertical forces are there? 1, 2, 3, 4, 5. The sum of all those 5 forces should be 0. The convention is the forces on the which are being exerted on the right side, they are taken as positive. So this force would be positive, x would be positive, and the force on the left side would be taken as negative. Similarly, the forces in the upward direction are taken as positive. This is another convention. this one would be positive, this one would be positive. In all the forces on the forces downward would be considered negative. Now for the horizontal forces, for forces on x-axis or for horizontal forces. Two forces are there on the right side, 10 Newton plus x Newton, and one force is there on the left side, which is 18. So x equals 18 minus 10, which is 8 Newton. And that makes sense. I mean, a force of 80 Newton is on the left side. Then on the right side, you have a force of 10 Newton. And there has to be an additional force. How much force should be there that the total sum on the right side is also 18? Well, the answer is 8. So you can do it that way as well. Now for the vertical forces. For vertical forces. So the forces on the upward, we write them on one side, and the forces downward, we add them on the other side of the equation. So 20 plus 30 on one side equals, what are the forces on the forces downward? Y, 25 and 10. We write them on the other side of the equal to. Y plus 25 plus 10. Now we can rearrange it to find the value of y. Y equals to 50 minus 35, and y equals 15 Newton. So you see the total force upward is 50. The total force downward has to be 50, but you have 25 here, 10 here, 35. What else do you need? You need 15 Newton, and that would be equal on both sides. All right, then we have the second condition. Second condition, I'm not going to study in detail, teach in detail, because we studied those details in the other chapter, that is turning effect of force. Or if you were done with it, then we would have studied over there. Now the condition number second is there should be no net moment of force. And if there is no net moment of force, the object will not be rotating. Alright, so this is not another thing. This is just the same thing. If there is no net moment of force, the object is not rotating. It can also be written as sum of clockwise moment should equal sum of counterclockwise moment or anti-clockwise moment. In that case, the object would also be satisfying the second condition of equilibrium. And if the object satisfies both these conditions, number one, there should be no net force. Number two, there should be no net moment of force. Then the object, we can safely say, is in equilibrium. So in this case, the seesaw is undergoing no rotation. If it is undergoing no rotation, it has satisfied the second condition of equilibrium as well, and the object would be in equilibrium. If the object satisfies one of these conditions, not the other one, then it would not be in equilibrium. Then we have the states of equilibrium and then types of equilibrium. For the states of equilibrium, we have these two states: static and the other one dynamic. So these are the two states for equilibrium. Static equilibrium is the state when an object is at rest and satisfies both conditions of equilibrium. Dynamic equilibrium is a state when an object moving with constant speed in a straight line or moving with constant velocity. And satisfy the two conditions of equilibrium. In that case, we say the object is in dynamic equilibrium. Then we have the types of equilibrium. There are three types of equilibrium: stable, unstable, and neutral. For the stable equilibrium, the object is said to be in stable equilibrium when it is tilted. The vertical line through its center of gravity passes through the base. For example, you have had the cone over here. If I try to tilt the cone a little bit, so it'll be looking something like this. If I try to tilt this cone, let's say something like this, this was the center of gravity of the cone, and the weight of the cone acts through this point and is always vertically downward. Now you notice one thing: this line of weight or the line of gravity still passes through the base of the cone. What's the base? This is the base of the cone, the part that was previously touching the ground or touching the object upon which the cone is placed. If you tilt it a little bit, and the base and the line of weight or the line of gravity still passes through the base, the object is in stable equilibrium. Then we have the other situation, unstable equilibrium. In this case, line of gravity doesn't pass through base. Now, what would it look like? So this is a cone. In this case, I try to tilt the cone a little bit. So after tilting a little bit, it will look something like this. Yeah, something like this. And this was, and in this situation, the base of the cone is this thing, because you see only a pointy part of the cone is touching the ground. is touching the table. So this is a cone. Now the weight of the cone is through the middle and it is vertically downward. And you realize that in this case, the weight of the cone is not passing through the base. This was the base and the line of weight is not passing through the base. In this case, we say the object is in unstable equilibrium. And when the object is in unstable equilibrium, you tilt the object a little bit, it does not return to its original position. For the stable equilibrium, if you tilt the object a little bit, it returns to the original position. And for the neutral equilibrium, the object's center of gravity remains at the same position when it is displaced. So its center of gravity is not lowered, or its center of gravity does not go higher. It remains at the same position. What are the example? A snooker ball moving on the snooker table, or a tennis ball rolling on the ground, rolling on the floor. Its center of gravity doesn't go up or down. It remains at the same place. And no matter if you touch the snooker ball or the tennis ball, it will remain at the same position. Its center of gravity will remain at the same position with respect to its original position. Now moving on to some of these sample questions. Here we have the first one. In which situation is the resultant force on the body equal to 0? A car turning a corner at constant speed, a rock falling freely on the moon, a train going straight up the hill at constant speed in a straight line, an aircraft accelerating along the runway in a straight line. So anyone who would like to answer this one? So C is the right answer. Very good. So C, we have the right answer. First of all, option A. What about option A is also saying a car turning at constant speed. So if the speed is constant, the forces might be balanced as well. So what is wrong with the option A? You see, there was one thing with the balance forces we said, and I mentioned it explicitly. If you're using the word constant speed, then you have to say constant speed in a straight line, which means with constant velocity. But when you're turning a corner, means you're not moving in a straight line. Your direction changes as you're turning. Your direction changes at every point. You have to make a turn. So this is not constant speed in a straight line. This is a problem with the option A. So the only thing that says constant speed in a straight line would have the resultant force. And when the object is accelerating, no chance for it to be with constant speed. And then we have a rock falling freely on the moon. Whenever an object falls freely, means it is falling vertically downward, it is accelerating, and its acceleration equals to gravitational field strength or gravitational acceleration, which is g, and for the moon it is 1.6 something. You don't need to memorize it. You need to memorize for the earth, which is 9.8 meter per second square or 9.8 newton per kilogram. How is the motion of a body affected by balanced and unbalanced forces acting on it? Anyone who would like to answer this one? Balanced forces, what happens to the velocity, and unbalanced forces, what happens to the velocity? Yes, very good. C is the right answer for this one. For the balanced forces, the velocity is constant, aka acceleration 0, and velocity changes, aka acceleration exists. Acceleration is not 0. Alright, then we have the next thing. Unbalanced forces cause should be cause object to accelerate. And when I use the word accelerate, it can mean decelerate as well. So unbalanced forces are the forces when net force is not 0, or the net force is there, or resultant force is not 0. And these are the situations. There exists a resultant force on the football, that's why it accelerates forward. There exists a resultant force in this situation. The force on this side appears to be more, that's why the system is accelerating on the left side. So there's no or in this. For the result, for the unbalanced forces, the object accelerates. Now these are the situations. You have a vehicle, there is a forward force called as driving force, which drives the car forward, and then there's a backward force that exists when the object starts moving, that is called air resistance. And you see the length of the arrows represent the magnitude of the force, because vectors can be represented by straight line and arrows, and the length of arrow represent the magnitude of force. So driving force appears to be more than the air resistance, object will accelerate. So driving force might be 500 Newton, the air resistance might be 100 Newton. In the second case, the driving force, this one, appears to be smaller than the air resistance, the object would be decelerating. The object slows down. So here we have elementary sample questions. The resultant force in the first case, F resultant equals the bigger force minus the smaller force. 5,000 minus 1,500. Alright, that equals to 3,500 Newton. Now the resultant force is there, and you have to mention the direction of resultant force as well, because force is completely defined by magnitude as well as direction, since it is a vector quantity. So 3,500 Newton where? To the left side. Then we have the other situation. We do have the resultant force, which is a bigger force 6,000 minus the smaller force 2,000. We're not following the sign convention. In A levels we have to follow the sign convention, so that one would be 4,000 Newton. The reserve force act on the car is 4,000, and the direction is towards right. All right, Newton's second law of motion, and this will be probably the last one for today. Newton's second law of motion corresponds to the unbalanced forces, and it says the acceleration of an object is directly proportional to the resultant force and inversely proportional to mass of the object. And then you have this thing: the greater the mass of the object, the smaller acceleration it is given by the particular force. And it's the other way around. So the force, mass, and acceleration can be combined to an equation. First of all, we said acceleration is directly proportional to resultant force, and acceleration is inversely proportional to mass. All right, if you combine these two things, you can write it down as F resultant equals mass times acceleration. So this is the thing that you need to memorize. Even if you don't memorize this one, that's totally not asked for the O-level exam, but you need to memorize the formula F resultant equals to ma. And I always use the word F resultant here. And you should refrain from saying F equals ma, because in some of the cases there are plenty of forces given. And then you have hard time in figuring out which force do you have to use in order to find acceleration or mass. And the answer is, that's why we write the resultant force. So let us solve some of these sample questions here. A block of mass 20 kilograms is pushed along a road with a force of 30 Newton. Now you have a force of 30 Newton, which is a pushing force, and the friction force of 10 Newton. The mass of the block is also given, which is 20 kilograms, and you need to find the acceleration. So first of all, we write down the formula F resultant equals ma. Then you can rearrange it to find A equals F resultant over mass, and F resultant, that's why we're writing the resultant. Now you know the resultant force means the overall force or the net force. So there's a force of 30 Newton pushing the box, and out of that 30 Newton, 10 Newton is being wasted against the friction. So what is the resultant? 30 minus 10, which is 20 Newton. So only 20 Newton is the resultant force divided by the mass. Mass was also 20 grams. So 20 divided by 20, and the answer would be 1 meter per second square, or ms minus 2.